Hello everyone. In this video, we are going to see Lenz's law. Now, Lenz's law helps us predict the direction of induced current, or you can say the direction of induced magnetic field in a conductor. Now, when is a current induced in a conductor? When is a magnetic field induced in a conductor? Whenever there is a change in flux. How can we bring about change in flux? One technique can be using a magnet. Okay, now this is a permanent magnet, and the magnetic field has been shown to you, the direction of magnetic field. If we move this permanent magnet either away from this circular coil or towards the circular coil, we are basically inducing a change in flux. Because of the change in flux, because of this change in magnetic flux, a current is going to be introduced, a current is going to be induced in this conductor. So Lenz's law basically helps us predict what would be the direction of current. That's all. What does it say? Lenz law or Lenz's law says that the direction of the induced current would be such that the induced current's magnetic field will oppose its cause. In other words, an induced current always flows in a direction such that it opposes the change that produces it. Now, what is the change which is producing this induction of current in this coil? That is the movement of this magnet. If there was just a coil and this movement and this magnet is going away from the coil, the flux is decreasing. The flux through this coil is decreasing. And it's decreasing in which direction? See, the magnetic field is like this, the magnetic field of the magnet. Now, this, as the magnet goes away, this becomes farther, farther, farther. Okay? So, the number of magnetic field lines reduce. The number of magnetic field lines in this direction reduce. This is the change which is producing the induction of current. Lenz's law says that now the induced current would be in such a direction so that it opposes this decrease in magnetic field. Decrease in magnetic field, okay? We can see this is the reason why there is an induced current in this. So once again, we are trying to recap how to find the direction of induced current. Because of the movement of this magnet away from this circular conductor, the magnetic field across this conductor in this direction keeps on decreasing. So magnetic field in this direction keeps on decreasing. So the induced current would be such that the induced magnetic field will try to oppose this change. What was the change? That change was a decrease in magnetic flux. So this induced magnetic field would be such that it tries to increase the magnetic flux or increase the magnetic field. So we know that the magnetic field, the induced magnetic field is going to be in this direction. How can we find the direction of induced current if we know the direction of induced magnetic field? Using Fleming's right-hand rule. So it says that if you curl your fingers in the direction of the current, you'll get the direction of the magnetic field. Now, we want the direction of the magnetic field to be this. So the thumb points out the direction of induced magnetic field that we need. So the curl of your fingers is going in this direction, right? And that would give you the direction of induced current. As you can see, this is the front side of your coil. And the back side, the current will go like this. So the current is going to flow round and round like this in this direction. So that is the direction of induced current. So it's coming down like this, and from behind, it's going up. That is the direction of induced current, okay? What would happen if instead of moving this magnet away from this coil, we brought it closer to the coil? Let's take a look at that. Let's look here now, okay? Instead of one single coil, we are going to take multiple loops, something like this, yeah? So we have kind of a solenoid, multiple conducting loops, one after the other like this. And here is a magnet being moved. Now the south pole moves towards this coil. South pole is moving towards this coil. And we know the magnetic field goes from north to south for the magnet. From north to south, like this, like this. Now, as this magnet moves towards the solenoid, moves towards this coil, magnetic field increases in this direction. Yes or no? I'll repeat the sentence. As the magnet moves towards the right, magnetic field in this direction increases. So B increases in this direction. So current in the coil would be induced in such a manner so that it opposes this increase. How can it oppose the increase in this direction? By introducing some induced magnetic field in this direction. Yes or no? So now we know that the current will flow here in such a way that the magnetic field is like this. Again, we use Fleming's right-hand rule to find out the direction of the current. We know magnetic field is in this direction. The curl of our fingers is going to tell us the direction of induced current in the coils. So these are the coils. The current is going to go like that, like that, like that, okay? So that means current must go up from here and through this coil just like this, like this, like this. This is how current will move and finally come out in this direction, okay? Again, a quick summary. Lenz's law tells us how to find the direction of induced current. Or if you know the direction of induced current, you know the direction of induced magnetic field as well. So this law gives us the direction of induced current or the direction of induced magnetic field in a coil, in a conductor, in a closed loop. Let's take this example now where the south pole is moved away. Now, this example is similar to the very first example, so we are going to skip that. We've already done this. Here we had just one coil or just one loop. Here we have many loops. That's the only difference. So if you're moving it towards, you're getting current in this direction. If you're moving it away, you'll get the induced current in the opposite direction. That's all, okay? So this is how we can use Lenz's law to find the direction of induced current or the induced magnetic field. Now, let's use this concept that we've learned today to solve a question which appeared in NEET exam in the last year. Let's take a look at that. So students, pause this video, read the question, try it on your own once, and then look at the solution. Let's look at the solution now. So we have a setup like this. There's a magnet here. This is the north pole, this is the south pole, and the magnet is moved in this direction. You can see this is the direction of velocity. There's a coil here, and there's another coil behind. Now we have to find the direction of induced current in both these coils, that's all. We're going to use Lenz's law to do that. South pole being moved towards this CD coil. If south pole moves towards this, we know magnetic field in a magnet is like this. If south pole is moved towards, basically the magnetic field in this direction is getting increased. To oppose this increase in magnetic field, there will be an induced magnetic field. There must be an induced magnetic field in the opposite direction. If there is an induced magnetic field in this direction, that tells me that the direction from Fleming's right-hand rule, that tells me that the direction of induced current is going to be in this direction. That means from D to C. So it's going to go from here, come down, come down, come down, come down, and come down to C. So in the second coil, in this coil, the direction of induced current has to be from D to C. That means this cannot be the correct one. This cannot be the correct one. It's either option 1 or option 4. Now let's look at this AB. Initially, the magnetic field, because of this magnet, is in which direction? From north to south. So initially, in coil AB, the magnetic field is in this direction, isn't it? If the magnet is moving away from the coil AB, this is decreasing. If the magnitude of this magnetic field is decreasing, induced magnetic field would try to increase it. So it would be in this direction. The induced magnetic field also will be in this direction because it's trying to compensate for that decreasing magnetic field. Now, once we know that the direction of induced magnetic field is this, we can find out the direction of induced current using the Fleming's right-hand rule. Again, we use our right hand. We know that this is the direction of magnetic field. The curl of our fingers is going to tell us the direction of induced current. So keep your hands like this. This is the direction of induced magnetic field. And you can see your fingers are going like this. So induced current is going from A to B. Okay, it's going like that, coming up again, going like that, coming like this, and coming out of B. So from A to B. So A to B. So that's why option 1 would be correct, not option 4. Okay. So this is how we use Lenz's law to find the direction of induced current in such a setup.